So section 9.7, we're going to calculate Taylor polynomials. Taylor polynomials get their name from a mathematician by the name of Brooke Taylor, although he's not the first person to study this. The first person to study this goes back a ways. Let me see, it's not here. Where is it? Madhava, and boy, I'm going to need some help with this. Sangam Magrama. Not sure. I don't know. Maybe somebody can help me with that. Anish, any insights? How would you pronounce that last name? No idea. All right. So I'm in good company. All right. He's an Indian mathematician. Lived around 350 to 425, and did some early work with this, but a lot of his work was lost, and the first person to actually publish some stuff about it was Brooke Taylor. And Brooke Taylor was a 17th century, 18th century mathematician. In any case, our goal here in working with these things is to try and approximate functions with polynomials. So let's take a quick look at some of the early problems here. Got these functions. Let's zoom out just a little bit. So, okay. So we've got this function which is e to the negative x squared over 2. And we want to approximate it with a polynomial. So we've got a bunch of different polynomials here, and let's see if we can't match them up. Some of them are better approximations than others. In particular, right here, that's a straight line. And if you look amongst your choices, only one of them is a linear polynomial. Really? So only one of them is to the first degree, and that would have to be the third one, because that's the only one of these that has x to just the first power. Let's look below that, down here with number C. Now, one thing that you can notice about number C, here's your function. In gray is the approximation. The approximation's pretty good for, a while, but eventually it takes off. Now, because of the way that it's shaped here, that both of these ends or these tails point up in the same direction, that tells you it has to be an even polynomial. So that's a little bit of a clue, as opposed to something like this, where the tail here points in opposite directions. This has to be an odd polynomial. How about this one? Even or odd? Even. Now the difference is here that both of the tails point down. So the leading coefficient here has to be negative, whereas the leading coefficient here has to be positive. So let's see if we can't finish our little guessing game to try and figure out which one is which. 3 went with A. Let's move up to 1. Which one does this have to go with? D. All right, you've got a negative leading coefficient with an even term, so they both point down. That's a good match. How about 2? This has to go with C. You have a positive leading coefficient and an even term, so those both point up in the same direction. And last but not least, B, this has to be an odd polynomial. Well, we've kind of run out of choices here. The only thing left is 4. But at least it is an odd polynomial. So, okay. What I want you to get out of this is a little bit of the look and feel of even and odd polynomials. Even polynomials, these tails are going to point in the same direction. For odd polynomials, they point in opposite directions. Okay. Let's skip on down to problem number 9. If it's okay with you, I'm going to help you do one of your homework problems. Is that all right? No one's going to get out and rate my professor and rant about me. Ugh, hated it. He always did my homework problems. Just miserable. All right, that's good. So let's take a look here. What I want us to do, we're going to enter in two equations into our calculator. The first one is a function. F of x is 4 over the square root of x. And then P2 is a polynomial. Now what's going to go on is P2 is going to approximate this function. We don't know how we get P2 yet. That's something we're going to work on soon enough. but it should be a good approximation. So let's do that. So in y1, I'm going to put 4 over the square root of x. And in y2, I'm going to put that polynomial 4 minus 2 times x minus 1 plus 3 halves times x minus 1 squared. You don't have to worry about what's in y3 yet. We'll do that together. I'm going to do a little experiment here. Now I got the headphones on, so I'm not sure if I don't think it'll play here, but you can tell me later if the Jeopardy music plays on the soundtrack here. It might help if I didn't have it muted. There we go. Alright, at least I hear it through my headphones. So, maybe it'll be on the soundtrack. Alright. Do you have this entered? We good? Yes, no? Alright. So let's see. In Arabic it'd be yella. In Spanish it's andale. In German it's mach schnell. In Hindi it's jaldi. What else? Spät. Bistreya. So a lot of places. Too sweet. Anyways. Alright, I think we've got enough time there on that. So let's kill the soundtrack here and go back here. Make sure that your table set up the right way. Second window, make sure that your independent is set to ask, and then we can type in our own values for x. So it won't matter where you start and what the increment is. Hit the second key, then the graph key to get a table. And now I'm typing in the values of 0.5 all the way up to 1.5. So why don't you do the same? And let's compare. Here's the value of the function. Here's the value of our polynomial. How are we doing with our polynomial? Is that polynomial giving us a good approximation of the function? It's not too bad. It actually changes. How does it change? For instance, right down here, how good's our approximation? It's pretty good. I'd say exact, right? You get 4 here, you get 4 here. So it's exact there. But as you move away from 4, you start to tail off a little bit. And to actually see that, one thing you could do is subtract these two functions. So let me show you how to do that, just in case you're ever curious. I want the difference of these two. Now I'm not going to type those two in again. That'd be kind of a pain. So if you hit the vars key right here, so next to the program key, next to the clear key, hit the vars key, then cursor to the right, hit y vars. I want function, so the first one, then type the number 1. So that's y1 minus, let's do y2. So y1 minus y2. So go back to vars, cursor to the right to y vars, press enter for function. This time select the second one down. You can just type the number 2. And what this is going to do is it's going to add another column. It's going to show you the error, how much of an error we're making in doing this kind of approximation. So let's go back to our table. It's adding that extra column. And there's a little bit of a pattern here with how much of an error we're making. Can you see what's going on here with the pattern? It's getting better and better and better, right? I mean, the error is smaller and smaller and smaller to a point. So we get to here. And then it starts increasing again. So, at least in absolute value. So basically, the best it can get is right here at 1. And when you move farther away from that, it's not as good. But that's the point. What I wanted you to see that this polynomial works best here at x equal 4. Excuse me, at x equal 1. The value is 4. So x equal 1 is what's called the center of this polynomial. And you can kind of see it in looking at the form of the polynomial down here. X minus 1 and then x minus 1 squared. So the value of x that would make this term disappear is 1. And that's the center of our polynomial. That's where this approximation is going to be the best. And in this case, it's actually spot on. Now, one of the amazing results that we yet to see in this chapter is something like this. Let me go all the way up here to the top. Let's see, I gotta ditch something here at the bottom real quick. Let's get rid of that and that. What I want you to do is try and recognize what this polynomial is as soon as you can. So let's set this down here to 0. So what I'm going to do is I'm going to add in terms to a polynomial one at a time. And let me list it for you, at least the first couple terms. I'm sure you'll see a pattern here that's fine. So the first couple terms look like this. X and then minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. Let's see if you can recognize the polynomial as I start adding in terms. So it helps out if I go over here. So here's when I have just the first term. Let's see. Oops, that's the wrong one here. Let's go down here. How about if I, there. So there's the first two terms, and then the first 3, 4, 5, 6, 7. Is this polynomial starting to look familiar? Looking pretty good. It's starting to look like the sine function. And if I add in more terms, it's getting closer and closer to the sine function. Now, eventually, it kind of tails off, right? But if I want it, if I want it better, then I can just add more terms. Just add more terms. Eventually, in the limit, this polynomial will equal a sine function. You can replace this polynomial for sine function. So it's just amazing that you can replace a transcendental function with this infinite series polynomial. So that's our goal. Our goal is to be able to create these kinds of functions. And let's see how it's done. Now, how it's done is in each of these terms, you're matching the derivative at a point. And by matching the derivative at higher and higher derivatives, you get a better and better Taylor series approximation to your polynomial. And then problem number 9, the center of our Taylor series polynomial was 0. Was 1. But when you're centered at 0, then you have a special Taylor series polynomial called a Maclaurin series. All right, so how do you find these Taylor series polynomials or Maclaurin series? Well, by matching derivatives, we can get something that looks like this right here. So our nth degree Taylor polynomial, we're going to have the value of the function plus a derivative at some point. That's the center of our function times x minus c to the first power, and then f double prime of c over 2 factorial times x minus c squared, etc. And this pattern is going to continue out to the nth term. So wow. Let's try that for the simple case when c is equal to 0. And we'll start with the function f of x equals e to the negative x in problem number 14. So that was an approximation to sine of x. We'll work with that again later. Problem number 14. f of x is e to the negative x. Now, one of the things that I saw that I needed in working with this Taylor series polynomial is I'm going to need a bunch of derivatives. So let's start out by finding the derivatives. In problem number 14, I think they tell us they want a n equals 5. So it wants to go up to the fifth term here. So let's start by finding some derivatives one at a time. So what's f prime of x going to equal? Good. Negative e to the negative x. And f double prime of x, e to the negative x. So hopefully you can see that this is kind of like the nice warm-up one, right? The derivatives here, successive derivatives, aren't that bad. F triple prime of x, it's just going to bounce back and forth between e to the negative x and negative e to the negative x. The other thing I don't need, in addition to the derivative, I actually need the value of the function at our center. Now with the Maclaurin series, the center is c equals 0. Maclaurin series are named after a Scottish mathematician, Colin Maclaurin. So at c equals 0, let's find all these values. F of 0, f prime of 0, f double prime of 0, and so on. E to the 0 is going to be 1, then negative 1, then 1, then negative 1, and so on. Now let's plug this into find our Taylor series polynomial, or actually Maclaurin series. So plugging it in, I'm going to start out with f of 0, and then f prime of 0 times x minus 0 to the first power, and then f double prime of 0 over 2 factorial times x minus 0 to the second power, and so on. It's going to keep on building from there. Now you don't have to write x minus 0, etc. But we do have to divide by the factorials. Technically speaking, there's divided by 1 factorial here. But what's 1 factorial? Just 1. So they didn't really list it there. That's okay. But I think I might, just to kind of get you in the habit of understanding this pattern here. So I want the 5th degree Maclaurin series for this. So I'll call it p sub 5 of x. It's going to start out with f prime of, or f of 0. Missing one of my implements of math instruction. So f of 0 plus f prime of 0 divided by 1 factorial times x to the first power plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and 2 more. X to the 4th and x to the 5th. Let's put in some numbers for these and see if we can't simplify them. f of 0 was 1 plus negative 1 over 1 factorial. So that'd be, well, instead of a plus there, let's just write a minus. You know, I'm going to take a little bit more time on this first one. Minus 1 over 1 factorial times x plus 1 over 2 factorial times x squared. And remember, up here, these derivatives are just going to be either 1 or negative 1. So it's just going to keep on alternating. Plus negative 1 over 3 factorial times x cubed plus 1 over 4 factorial times x to the 4th minus or plus negative 1 over 5 factorial times x to the 5th. Now, depending on your need, you can expand these and write it as 2, 6, 24, 120, etc. Sometimes it's handier to keep it as a factorial so that you can see patterns in your expansion. Did I make a typo in this third term here? I just wrote it 1 over 2 instead of 1 over 2 factorial? Yeah, they're the same. So 2 and 2 factorial are the same. So that's your 5th degree Maclaurin series approximation to e to the negative x. Let's see how it looks. Let's see how we did. So let's cancel this out and look at problem number 14. Let's see, I need to cancel out one more. Let's get rid of that. And let's see, I think there's a couple more. I don't want to see that. And I want to see that right now. Okay. So let's go back up here, problem number 14. Here's our function. Let's see how good our series does in approximating this function. So there we go. So it's not too bad near 0, right? I mean, near 0, there's not too much daylight between these two curves. So here's our approximation. There's the curve. So pretty close. Now, the farther away you get from 0, the farther away you get from your center, what happens to the approximation? It's less and less good, and eventually you can start to see a lot of daylight between your approximation and the actual true value. But near the center, you're pretty spot on. How are we looking on that first one? Okay. Rousing applause. Thank you. I hope that was picked up by the mic. Let's try some more here. Problem number 18. Let's just some questions on this one. It's going to be the same kind of thing, just a different function. So what we just put together right here, this is an approximation. It's a pretty good approximation as long as you're close to 0 of e to the negative x. Now, so what's the point though? What's the advantage? Well, think about all the work that you've done in calculus with differentiation and integration. What's easier to work with? Polynomials or functions like e, sine, and cosine? Polynomials, hands down, right? They're easy to work with integrating, differentiating, etc. So if you can replace some of these functions by simple polynomials, wow, it's a win. And it allows us to do more and more things too. For instance, when you hit the sine button on your calculator, how does it get that number, you know? How does it know what those values are? I mean, at some point, they got to program it to do something. So this is starting to give you a little bit of insight as to how they can get, you know, sine of 3 pi over 7 or something like that off your calculator. There's actually a long ways to go before we get there, but at least it gives you a little bit of an insight. All right, thanks, Jared. Let's take a look at problem number 18 then. F of x is cosine of pi x. Again, it's going to be a Maclaurin series, which means the center equals 0. That's kind of unsaid. If it says Maclaurin series, then it automatically follows that c equals 0. This time we want a 4th degree polynomial. It'll tell you that in the problem. It'll just say n equals 4. One thing I want us to notice about the cosine function here. Let's see. So let's shut these off. And let's come down here to problem number 18. The one thing I want you to notice about the cosine function is that it's symmetric with respect to the y-axis. There's a fancy mathematics term for that. If something's symmetric with respect to the y-axis, what do we call those kinds of functions? Other odd. Even, yeah. Even functions. Yeah, so they're even functions. They're symmetric with respect to the y-axis. Now, I want you to keep an eye on what happens with our Maclaurin series approximation here, because the evenness of our function is going to be reflected in our polynomial. Let's see how and why. Okay. How about the first derivative? Negative pi times the sine of pi x, right? Derivative of cosine is negative sine times the derivative of the inside, which is pi. So negative pi sine of pi x. Cool? Liam, how about the next one? Good. When you differentiate again, we're going to get the cosine back, but we're going to get another factor of pi multiplying out here. So cool. Trevon, how about the next one? F triple prime. Nice. Notice that Trevon gave me a positive one here. Kevin, the last one. Thank you. Pi to the 4th cosine of pi x. Great. Let's find the value of this function at the center here. So f of 0, f prime of 0, f double prime of 0, f triple prime of 0. And I can't make my voice any higher, at least not voluntarily. So we'll just leave it there. Let's see. Anish, what's f of 0 going to be, please? 1? Good. Rand, how about f prime of 0, please? Zero. Because sine of 0 is 0 times negative pi is still 0. Okay, that's fine. Let's keep going. Con? F double prime of 0? Minus pi squared. Noor, f triple prime? 0. Good. Is it Vicky? Can't see behind Elizabeth there. There you go. Vicky. And pi to the 4th. Good. Let's put that into find our Taylor series, or excuse me, it is a Taylor series centered at 0. The Maclaurin series approximation is probably better stated. So p sub 4 is going to be f of 0 plus f prime of 0 over 1 factorial times x to the 1st power plus f double prime of 0 over 2 factorial times x squared. The only reason I'm writing this is for you to start to memorize this pattern here. You don't have to write it necessarily as you do these things in your homework. It does help out a little bit maybe, and it certainly helps me if I can follow your work a little bit better. F of 0 was 1 plus 0 over 1 factorial times x plus negative pi squared over 2 factorial times x squared plus 0 over 3 factorial times x cubed plus pi to the 4th over 4 factorial times x to the 4th. You know, I forgot the x to the 4th up there. My bad. The nice thing is that a couple of these disappear. That one disappears. That one disappears. So overall, you're left with a pretty simple function. 1 minus pi squared over 2 times x squared plus pi to the 4th over 4 factorial times x to the 4th. So not bad. Do you see anything here that reflects the shape of the cosine function here? It's not quite worth it. It's even, yeah. Take a look. All the odd terms dropped out. You have an even function, so it's being matched by an even polynomial, which makes sense. If this was a sine function, all the even terms would drop out. We'd have all the odd terms left. So, yeah, it matches it. Let's see how good it does. So, here's your cosine. Let's see our polynomial. Not bad. I mean, until you get to about negative 1/2, the polynomial is not too bad. But certainly, the closer you are to the center, the better it is. I mean, if you zoom in a lot, boy, you're just not seeing much daylight between these two functions. Just not. They're pretty similar for a while. Eventually, what we're going to have to do is we're going to decide, well, gee, how far out do I have to go? How many terms do I have to go, you know, to get a good approximation? So that's on the horizon, but it's a ways off. Right now, we're still working on practicing how to find these things. Is he starting to make a little bit more sense? Could you tell your friend when you go home tonight, what did you do? Calc 2 class? Oh, I don't know. Tweet about it in 140 characters or less. Is it 280 now? Yeah, but they stopped before 288, right? It's too gross. All right. Yeah, it was very close to gross. All right. Let's try some more here. This one is one that you should try, and I'll give you a little bit of help. It's problem number 22. F of x is x over x plus 1. So that's the function. Again, it's centered at 0. C equals 0, so it's a Maclaurin series. You're going to need a succession of derivatives. I'm going to help you out with the first one, maybe two. The first one looks like this. When you differentiate this, you get 1 over x plus 1 squared. Now, you can do yourself a huge favor if you rewrite this as x plus 1 to the negative second power. Why? Why is that a huge favor for you? Yeah, you don't need to use the quotient rule, right? Yeah. I don't want to see too many people going, oh, man, Can we please use a quotient rule? All right, it's just not happening out there. So this way, you can use the power rule. And the chain rule a little bit, I guess, but derivative of the inside is 1. -2 times out in front, x plus 1 to the -3rd power, and so on. You're going to need a couple more derivatives. Then try and finish it up and write our Maclaurin series approximation. Degree equals 4. So you need 2 more. F triple prime Did I tell you about the Carl Frederick Gauss? His class, when his teacher got mad at him? Is that the one to the 100? Yeah. Figure it out. Yeah. So, I think Gauss, I've heard various versions, he was either 7 or 10 years old. His teacher got mad at class and told him to add up the numbers 1 through 100. And everyone's working away furiously at it, and Gauss just threw his chalk slate on the teacher's desk, and it had one number. And it was the right answer. 5,050. Pretty impressive for a 7 or 10 year old. That was scrumptious. Did she share something with you? Okay, so let's finish this up. The next derivative is going to be 6 times x plus 1 to the negative fourth, and then negative 24 times x plus 1 to the negative fifth. Plugging in 0 is pretty nice because it's not that hard. Here I get 0, here I get 1, here I get negative 2, and then 6, and then negative 24. I think I got all those right, yes. So it's going to be 0 plus 1 over 1 factorial times x minus 2, or plus negative 2 over 2 factorial times x squared plus 6 over 3 factorial times x cubed plus negative 24 over 4 factorial times x to the fourth. Now I think a lot of you caught this simplification here, right? Did anyone else see it? That's going to be x minus x squared. What happens here? Plus x cubed. And these cancel as well. Minus x to the fourth. So, wow. Not too bad. In fact, you could probably take a wild guess as to what the next term would be, right? What do you think? Yeah, plus x to the fifth, right? So it's kind of nice. There's a pattern here. And in this case, we wouldn't really have to just restrict ourselves to p sub 4 if we didn't want to. We could do p sub infinity. We could actually get all the terms. So replace this with an infinite series polynomial. So, nice. Okay. Let's see. Let's start shifting away from a center at x equals 0. Let's start doing a couple calculations when x equals something else, like in problem number 26. So let me get that out here for us. Yep. All right. Still got sound. Wow, I was kind of annoyed that last week some of mine didn't come out. So for 26, here's what we got. F of x is 1 over x squared. N equals 4. And this time c equals 2. So we're no longer doing a Maclaurin series because we've got a different center. That's okay. We're still going to start out by calculating a bunch of derivatives. It's probably in our best interest to rewrite this as x to the negative second. So that way we can calculate our succession of derivatives a little bit faster. So f prime of x is going to be negative 2 x to the negative third. F double prime of x is going to be 6 x to the negative fourth. And then triple prime, negative 24 x to the negative fifth. And finally, 120 x to the negative sixth. A little bit more work to evaluate our function this time because instead of plugging in a 0, what am I going to be plugging in? 2. All right, so let's see here. 2, 2, 2, 2, and 2. And that comes from right here. So it's going to be 1 over 2 squared, or 1/4. This will be negative 2 over 2 cubed, which would be negative 1/4. Here I'll get 6 over 2 to the fourth. So 6 over 16 reduces to 3/8. Negative 24 over 2 to the fifth, that's 32. So negative 3/4. And the last one is going to be 120 over 64, which 8 goes into both of those, so that's going to be 15 over 8. Whew. All right, not too bad. If you're stuck on some of these, if you're like, I don't know, I don't want to reduce 120 over 64, just a little reminder here that your calculator can come to the rescue. If you do 120 divided by 64 and you don't recognize that, hit the math key, then press enter twice, and it'll give you a nice neat fraction out of that. So don't strain your brain too much on that part. Save it for other things in these types of problems. All right, let's see about filling this in. Do I need to give you the general form here? You know what, maybe I should, because we got a different center this time. So it's going to look like this. P sub 4 of x is going to be f of 2 plus f prime of 2 divided by 1 factorial times x minus 2 to the first power. And then these terms continue. Plus f double prime of 2 over 2 factorial times x minus 2 to the second power. 2 more. Plus f triple prime of 2 over 3 factorial times x minus 2 cubed. And then last but not least, f to the fourth power of 2 over 4 factorial times x minus 2 to the fourth power. Sorry, I'm kind of running out of room there at the edge. All right, let's fill this in then. F of 2 was 1/4 plus negative 1/4 divided by 1 times x minus 2 to the first power. F double prime six over 2 to the fourth. So it's 6 over 16. So I'll stick with the 3/8, but I appreciate you checking me there. Thanks. It did look like 6 over 24, which would have been 1/4. You're right. F of 2, or f prime of 2, double prime of 2, I should say, is 3/8 over 2 factorial times x minus 2 squared plus negative 3/4 divided by 3 factorial times x minus 2 cubed. And finally, f to the fourth was 15 over 8 over 4 factorial times x minus 2 to the fourth. I would appreciate you cleaning it up a little bit. Not really fond of getting it like this. So let's see if we can't do that. That's 1/4 minus 1/4 times x minus 2. 3/8 divided by 2. Well, it's 3/16 times x minus 2 squared. If you're not sure with these, again, I mean, you can use your calculator, and let's be clever about this one. 3/4, that's negative 0.75. So we'll skip the negative part. We know that. 0.75 divided by, what was it? 3 factorial. 3 factorial is 6. And then hit the math key if you don't recognize that. That's 1/8. Okay, cool. So minus 1/8. Yeah, let's make that a minus. Minus 1/8 x minus 2 cubed. And the last one, you invert and multiply. Let's see what's going to happen. You have, I don't know, 15 divided by, what's that going to be? It's 160, whatever. Let's do it this way. 15 divided by 8 divided by 24. Math key, answer to fractions. 5/64. Yes! Woohoo! All right. Plus 5 over 64 x minus 2 to the 4th power. So wow, kind of ugly, but you know, it is what it is. That's our polynomial. So in the neighborhood of x equal 2, as long as you're close to x equal 2, this polynomial will give you a reasonable approximation to our function. Hans?
When you want it cleaned up, do you always want us to take out the factorial?
Yeah, you know, it's helpful. I mean, it depends. Sometimes leaving in the factorial leaves you a pattern, and it's nice to see that pattern. In this case, because we're just working with a finite polynomial, the 4th degree polynomial, that's why I simplified it. But in other cases, like the last one, you know, sometimes leaving it in is helpful. You can kind of see it. In fact, if I wanted to, I could have written this with polynomials, or I mean, with factorials here. You could have seen the cancellation a little bit easier. That's all right. We eventually figured it out. Anything else on problem 26?
If we had center at -2, we would have x plus 2, right?
Yeah, if you had a center at -2, x minus -2 would end up being a plus here. So, yeah, great question. Let me see if I got that one pre-programmed in here. Let's ditch that one. Yeah, here we go. So there's our function. You can see it's got a vertical asymptote at x equals 0. Let's see how our polynomial does. Our polynomial, remember the center is at x equal 2. So it's near x equal 2. Let's show that point. It's near here that the polynomial is going to do pretty good. And as long as you're reasonably close to the center, we actually do get a good polynomial approximation. I mean, I can zoom in quite a lot, and there's really no difference between those two functions that we can see. Keep in mind at this scale, each one of these is 1/10. So whatever difference there is, it's much, much, much less than 1/10. Are you starting to understand why we would shift the center? Well, maybe not. Let me try and explain why we would shift the center. I mean, why bother at all? For instance, suppose I wanted to approximate the sine of 20. Well, I've got a perfectly good series to approximate sine functions. That's the one that I showed you way back at the beginning here. But take a look at what I would have to do to approximate the sine of 20. So let me put that back here. So let's plot that point. And let's see. So 20 is way out here. So it's a pretty far, well, not terribly far, but it's a ways out on the x-axis. And remember, the center of this polynomial was at 0. So let's dial that down. There's essentially a tangent line, a first-degree polynomial approximation. Let's add in some terms. A equals 1, 2. How many terms do I have to add before I get a good approximation? So I'm at 15 terms. Do you think this polynomial is going to give me a good approximation to the sine of 20? No, probably not. 17, 20, still not there. A little further, 25, yeah, getting there pretty good. So 25, 26, 27, that's a lot of terms. I mean, it's a really big polynomial. And one of the things you don't really appreciate is just the size of some of these numbers underneath here. Remember, that's 2 times n plus 1 factorial. Now let's just take a modest number like 20. 20 factorial is huge. If you were to write out 20 factorial, you'd probably want to use scientific notation. So 20 factorial is 2.43 times 10 to the 18th power. I got to stop and think about this. 10 to the 6th power is millions. 10 to the 9th is billions. Then trillions. Then quadrillions. Then quintillions. Is that far enough? Let's see. 6 is millions, billions, trillions, quadrillions, quintillions. So 2.43 quintillion is 20 factorial. That's a huge number. You don't really see it, but your calculator is really screaming, straining to handle these kind of numbers. They're huge. And that's not even the biggest one. I mean, we have 54 factorial when you're getting all 54 and 55 factorial. That's going to go well beyond my vocabulary, I guarantee you that. 55 factorial. 73. 1.269 times 10 to the 73rd power. For comparison, the number of protons in the universe is thought to be around 10 to the 80th power. So this is a remarkably large number. And it's, you know, it'd be nice if you didn't have to deal with something so huge. And remember, that's just one term out of 27. So to try and use the sine series centered at 0 to approximate this, it's not really a good idea. You're using a lot of terms, a lot of computing power to do that. So instead, let's shift the center. And what I'm going to do for you is a little bit of math to help you figure out where a good place is to shift the center. So let's do, it's helpful to have something that's a multiple of pi. So here we go. Let's take 20 and divide it by pi. Oops. 20 divided by pi. And I get about 6.33 or 366. So out of convenience, let me just round that to 6.25. Let's just say 6.25. Okay, that's somewhat close. I don't have to be spot on. So 6.25 pi, well, that's not too far away from 20. That's certainly a lot closer than a center at 0. You can pick other centers. I could have used 6 1/3. That would have worked out fine as well. But let's use 6.25. Or 6.25, answer to fraction, is 25 over 4. So that's our center. So here's our mission. F of x is the sine of x. Our center is 25 over 4 pi. And I want the first 4 terms. 25 over 4 pi is 6.25 pi. And it's helpful to note that because that's also 6 pi plus 1/4 pi. 6 plus 1/4 or 6 1/4. So let's just keep that notion handy for a little bit. We need to start some derivative work again. F of x is a sine of x. I'm hoping that the derivatives here are pretty simple. We got to go down to the 4th derivative. And we get back to sine of x. Now what? Yeah, now we got to plug in this point into our function because we got a different center. It's not 0 anymore. This is not a Maclaurin series. It's a Taylor series centered right here. So let's see what that's going to be. That's going to be f of 25 pi over 4. Now let's stop and think about the unit circle for a moment. When we evaluate things on the unit circle, really what we care about is where we end up. And if you make a couple extra laps around the unit circle along the way, it doesn't really matter. So, as far as the unit circle is concerned, I wish I had something better here. But here's what's going on. Once around the unit circle is 2 pi, and then 4 pi, and then 6 pi. So 1/4 pi is a 45-degree angle. So really you're evaluating your sine and cosine functions at that pi over 4 angle. What's the sine of pi over 4? Root 2 over 2. Trick question, what's the cosine of pi over 4? Root 2 over 2. All right, so yeah, they're both the same because you're on the line y equals x there. F prime of 25 pi over 4. So again, root 2 over 2. F double prime of 25 pi over 4. Negative root 2 over 2. Negative root 2 over 2 again. And finally, root 2 over 2. Whew. All right. Let's come up with our Taylor series approximation then. So P sub 4 of x is going to be f of c plus f prime of c over 1 factorial times x minus c to the first plus f double prime of c over 2 factorial times x minus c squared, and so on. That should be fourth of c over 4 factorial times x minus c to the fourth. C in this case is not a very pretty number, right? It's 25 pi over 4. That's okay. F prime of, or excuse me, f of 25 pi over 4 was square root of 2 over 2 plus square root of 2 over 2 divided by 1 times x minus 25 pi over 4. F double prime is negative, so negative root 2 over 2 over 2 factorial times x minus 25 pi over 4 squared minus root 2 over 2 over 3 factorial times x minus 25 pi over 4 cubed. And last but not least, root 2 over 2 over 4 factorial times x minus 25 pi over 4 to the 4th power. If you're interested in cleaning this up, it actually does clean up okay. You could factor out the root 2 over 2 so you didn't have this on all your terms. So it'd be root 2 over 2 times 1 plus x minus 25 pi over 4 minus 1/2 times x minus 25 pi over 4 squared minus 1/6 times x minus 25 pi over 4 cubed plus 1 over 24 times x minus 25 pi over 4 to the 4th. Get out the oxygen bottle, right? At least give me some ice for my wrist. Kind of a pain, but this is a lot nicer than some term that involves numbers like 2.43 times 10 to the 18th power, 2.43 quadrillion, and bigger. I mean, that just becomes a real immense problem to calculate. And actually, we probably didn't need to go this far. Let me pause here before we look at the graph and see how this one does. But the calculation here is what I'm after. What's what I'm after. I want you to be able to follow how to get this. How are we doing on that calculation part? It's hard. It's just a lot of tedious work. Yeah, there are. But don't worry, if you make a mistake, I'll simply mark it wrong. Sorry. All right. Let's see how our polynomial did. So let's shut this one off and go down here. So here's our point. There's our polynomial. Now, it's not really good near 0, but it looks pretty good out here at x equal 20. In fact, let me see if I got it up here. Where is it? I don't. Oh, let's just put in sign there. So it looks pretty good near where it's supposed to. In fact, my guess is that I probably didn't need 4 terms. I might have been able to stop with 2 or 3 terms. So let's take a look here. What I'll do is you know what? This only has 2 terms. Wait, or 3 terms. Wow, it doesn't even have all the terms. Where'd the rest of them go? All right, wow, this is even better than I realized. Look, so this one doesn't have as many terms as I thought. Somehow or another, I lost a couple because I did program it all the way in. But even with just a quadratic approximation, that is going out to the squared term, you're getting a pretty good approximation of that number with just a few terms. So it's much better than using the unshifted series. Now on an exam, if I asked you why shift a series, then the answer is twofold. So let me write that down here for you. And if you get it wrong, I'll point you back to the video. Why shift a series? Why should we work with a different center? Well, you get better accuracy with fewer terms. And in our case, much fewer terms. I mean, 2 or 3 terms of a second or third degree of polynomial as opposed to a 27th degree polynomial. Wow. And that's just crazy. Okay. One of the things I relearned recently is that, I mean, to really learn something, you got to practice it. You got to do it yourself. So let me give you a problem to work on. But here's the little carrot for you. It's one of your homework problems. So why don't you try problem number 29? So f of x is ln of x. We want an n equal 4 degree polynomial, and want that approximation centered at c equals 2. So good luck. unpause it? There we go. Unpause. Oh well. Okay, so our succession of derivatives looks like this. Derivative of log is x to the negative first, or 1 over x. I'd write that as x to the negative first, and then it becomes easier to do your derivatives. After you get your derivatives, it might be in your best interest here, Andrew, to rewrite that as 1 over x squared, or 2 over x cubed, or negative 6 over x to the fourth. Then it becomes easier to plug in your values like x equal 2 into these terms. Now, this one doesn't simplify. It's just log of 2. That's all right. At the first derivative, I'll get 1 over 2, and then negative 1 over 4. Positive 2 over 8 reduces to 1/4. And then negative 6 over 2 to the fourth, that's 16, so that's negative 3/8. So those are all my functional values. Let's put these in to this formula down here. See what happens. P4 of x is going to be the ln of 2. But remember, that's just a constant, so that's okay. F prime of c divided by 1 factorial, so it's going to be 1 over 2 divided by 1 factorial. X minus 2 to the first power, minus 1/4 over 2 factorial times x minus 2 squared, plus 1/4 over 3 factorial times x minus 2 cubed, minus 3/8 over 4 factorial times x minus 2 to the fourth power. And if I clean that up a little bit further, ln of 2 plus 1/2 x minus 2 minus 1/8 x minus 2 squared plus, that'd be what, 1/24 times x minus 2 cubed minus 3 over what? 3 over 72. Actually, the 3 should cancel, right? So it would be 1 over 24. 3, 2. Oh, man, let's see. Well, the 3 and the 3 here will cancel, so I'll be left with 2 times 4. Yeah, 1 over 48. Is that right? I don't know. All right, I'm a little brain dead, just kind of like you guys are. So 0.375 divided by 24, math, 1/64. Is that what you guys are getting? All right, 1/64. X minus 2 to the fourth. Yay. How are we looking on this one? Feeling comfortable on that one? All right, let me give out some homework. For homework, try 1 through 37.